Thank you. It's great to be here. Although there was a little bit of bait and switch. I came in last night. It was beautiful outside. I took a walk. I woke up this morning and it's different. And I hear that there's a high school class of students here. Great. It's great to have you here. Welcome. What I want to talk about this morning is machine learning, but it's not what you think of when you think of machine learning. So sometimes if you think about machine learning today, it's pretty much computers plus statistics plus big data. But if you want to know the future of machine learning, I think all you have to do is make a list of the ways that humans learn that people don't yet. So we surely, as people, we learn statistically. We look at data. Our brains notice regularities. We learn that way. But there are a lot of other ways we learn. One of them is we go to school, or we go to lectures, or we have conversations. And so what I really want to talk about, I know there's nothing on this slide, that's because I want you to look at me. What I really want to talk about is something that we don't have in the field today, but I think is going to be the single most important advance in machine learning over the next decade, or maybe advance is the wrong word, trend is, I think, the word I'm looking for, which is this. Today, we finally, after decades of research, have phones and other kind of computers that can understand our speech and have conversations with us. Right now, we think of using those conversations with our phone to call up the kind of functions that we know the phone can do. So we say, hey Siri, what's the weather today in Toronto? And it tells us. Oh, I didn't mean to do that. It's currently. Or we say, you know, who won the football game last night, or whatever. And it tells us. We're still in the mode, we're going to change. But us humans, we're slow to notice that now that we can have conversations with machines, we can do more with those conversations than simply call up the capability that the phone already has. And so the goal of the research that I want to talk about today is really to make everybody a programmer. So if I ask you today, what fraction of humans can add a new capability to this phone by programming it? I don't know the answer either, but I'm sure it's less than 1% of humans on Earth, because those are the people who took the time to learn the language, the programming language of the computer, and they know how to program it. Many of them are employed by Apple or Google or somebody. They're the people who can change the function of the phone. What I want to do is pursue a line of research where instead we end up with a world where 99% of people can program the phone. But it's not by teaching everybody the language of programs. It's by teaching computers to listen to instructions and getting people to program by teaching. So for example, if I'm your assistant, if you were to hire me as an assistant, you wouldn't really, I'm lucky, I have a human assistant. And if what she did was passively observe me to get thousands of examples to figure out statistically what she thought she should do for me, I would have fired her last month. Instead, we talk to each other. And I walk into her office and I say, hey Mary, this semester I'm going to be team teaching a course on deep reinforcement learning. I'm forwarding you an email that has the names of the teaching assistants and a pointer to our website. And here's what I want you to do. Whenever there's a new homework assignment we're about to hand out, I want you to make sure that it gets pre-tested by the teaching assistants at least 2 days before it's due to be handed out. Okay, so that's the kind of programming by teaching that I do with my human assistant. And if you think about it, there's no reason why we shouldn't try to give our phones the same capability to be taught. So this is really the motivation for the research that we're doing, trying to make it possible for everybody to be a programmer, not by learning computer languages, but by having computers learn to be taught. Okay, so how do we frame this problem? In general, I'm going to say we have some kind of sensor effector system. It might be a mobile phone, in which case the sensors are things like microphones and cameras, physical sensors, but also electronic sensors like a web browser can sense the state of the external web. And it has effectors. Some are, again, physical. It can vibrate. But some are electronic, like it can send email or text messages. So in general, I'm thinking we have some kind of computer system with sensors and effectors into the environment. And of course, this could also be a robot. Then it would be a different set of sensors and effectors, wheels and cameras and microphones and so forth. But in either case, we could think of such a system. And then what I want to define is what I'll call the sensor effector closure of this system. What do I mean by that? It's just a fancy way of saying, think of the set of all the operations this agent could perform in its environment, given that it only has this set of sensors and effectors. And if you think about, for example, your phone, and think about the sensors and effectors that it has, then in principle, there are a lot more things it could do than the things that happen to be programmed today. So the point of the research, the goal of the research in general is, given a sensor effector system, the goal of the research is to make it possible for users to teach the agent anything, to do anything that's in that sensor effector closure, anything that is physically possible for that agent given the sensors and effectors that it has. So what are some of those things for a phone? Well, for example, I'd like my phone, and in this case, this is something that an engineer at Google actually thought of. So my phone does have this procedure in it. Whenever I have to catch a flight, alert me to head to the airport in time so that I arrive before the flight takes off. Some engineer in Google apparently thought of this and put it into an app that you can download, and that's a useful thing. It's in the sensor effector closure of my phone. It's something that's possible in principle, and in fact, somebody implemented it. But there are a lot of others. Whenever it snows at night, wake me up 30 minutes early. That's certainly feasible given what we know phones can sense. They have weather apps. They can sense the weather. They have alarms. They can certainly do that. But nobody happened to write this program yet. I'd like to be able to teach it. If somebody sends me a picture of my mom, forward it to her. If a student sends me an email about a homework question, forward it to the right teaching assistant, the teaching assistant who wrote that question. So these are all things that are within the sensor effector closure. If I had an easy way to program by teaching my phone, these are some of the things I would teach it to do. Okay, so in general, here's the formalization of the problem. We assume, Leah, by the way, is our learning by instruction agent. And so the formalization of the problem is we're given an agent with sensors and effectors, and we assume that agent also has an initial natural language competence, which allows me to speak to it to invoke each of those primitive sensors and effectors that it has. So if the phone has, let's say, an accelerometer, I should be able to say to it, what's the reading of the accelerometer as part of its primitive language capability. And then we want the system to learn really 3 different types of information or knowledge. One is, it's going to have to improve its language over time, because the truth is computers today don't really understand natural language very well. It's going to have to learn new procedures like the ones that I'm teaching it. those procedures have to be grounded in its sensors and effectors. So if I say, whenever it snows at night, wake me up 30 minutes earlier, for that to be learned as a procedure, the agent is going to have to come up with a piece of code that grounds out in primitive calls to these sensors and effectors available. And then finally, the system's also going to have to learn a bunch of background knowledge about the world, about me, about my goals, just so that in the same way that if you and I speak and I know about your background, I can understand better. So for example, I want to be able to say things like, define the concept of a course. A course has a title, instructors, teaching assistants, students, and a semester. And then I want to be able to say one course is Tom's Fall 2018 Deep Reinforcement Learning class. So these are the three kinds of things that we think the system is going to have to learn. Okay, so we have a little prototype of such a system, and I want to play you a video, which never works if I try to embed it in there, so I'm going to play it here. And what you'll hear is Igor Labatov, one of our postdocs, having a conversation with the system where he teaches it to do a couple things. The first thing, he'll give it some facts, but then well, you'll see. I'll just play this.
Katie is a new member on the project team.
Katie is a member of the project team, right?
That's right.
Okay, I made Katie a member of the project team.
Tell my project team we will meet at 4 p.m.
I don't understand what you mean by tell my project team we will meet at 4 p.m. You can explain or demonstrate if you want to teach me, or just rephrase.
Okay, I'll teach.
Great. Please break it down for me to steps so I can learn.
All right, first create a new email.
Compose a new email, right?
Yep.
An instance of type email created.
Then set its recipient to the email address of everyone on my team.
Set recipient field of email you created with the email address fields in project team's instances, right?
That's right.
Got it.
Then set its subject to we will meet at 4 p.m.
Setting subject field of email you created that we will meet at 4 p.m.
And send it.
We'll execute send this email. Got it.
That's it.
Great. I learned how to tell my something or someone something.
Okay, so what you just saw there is he started by saying something like, tell my project team we're going to meet at 4. And the phone said, I don't understand, which is the same response I get from my phone. But then it said, do you want to teach me? And he said yes. And so then he broke it down into these smaller steps. Create a new email. In the recipient list, put the members of the project team. In the subject line, put this, send it. So what he did was literally taught a new procedure to the phone. And so that if he were to say exactly that sentence again, tell my project team we're going to meet at 4 p.m., now it would know how to execute that. But in fact, the system also generalizes to some degree from this example, so he can say other things.
Tell the assistant I will be busy at 4.
Okay, tell the assistant I'll be busy at 4.
Tell your assistant you will be busy at 4, right?
That's right.
Executing tell my assistant I will be busy at 4.
Okay, so this time it understood. Just like tell my project team we're going to meet at 4, he had to instruct it. But now that it has learned from that episode, one episode, it's able to parse and execute, tell my assistant that I'll be busy at 4. Okay, so it's a simple example, but it gives you the idea of what we're after. So let's drill down a little bit and see what really happened in that episode. So here's the transcript. First, Igor said, Katie's a new member of the project team. That's just to illustrate that you can give the system background facts and it'll store them in its long-term memory. But then here's, tell my project team we'll meet at 4 in the breakdown. If we continued that movie, you'd see that there's another episode where he teaches a conditional statement. If this happens, then do this. If I get an email from my project team, then forward it to my assistant. And again, in this case, the agent didn't know what it means to get an email from my project team. And so, again, he was able to instruct the system to teach it what it means to detect that we get an email from the project team. Okay, so how does this system work? It's actually built on a natural language parser, a semantic parser, which maps the recognized text strings from, we use Google speech recognition. There's nothing non-commercial about that, nothing researchy or fancy about the speech recognition. We just use Google Speech, which then gives us the text. But the interesting part is how do we take that text string and turn it into a procedure? So in our semantic parser, when it parses prepare an email to Bill, the result of the parse is an executable piece of code like do in sequence, create an email, and then set the recipient to Bill. In our learning by instruction agent, this logical form that describes the semantics, it's grounded in those agent sensors and effectors, so that if you evaluate the code, it'll actually operate the sensors and the effectors to achieve what the natural language command is. And in this semantic parser, the system both builds a syntactic parse and a semantic parse at the same time. So for example, a syntactic parse would say, if you have an adjective followed by a noun, call that a noun phrase. The red house becomes a noun phrase. But at the same time, that parse rule composes the meaning of the phrase out of the meaning of the component parts. And so that same rule will say, take the predicate, which is the adjective meaning, and apply it to the noun. So it gives you a semantic form. And then in the end, Leah ends up learning by redefining its grammar. So when you saw Igor teach by saying, oh, the way you tell my project team this is by creating an email and then putting the recipients list, filling it in this way and filling in the subject, it's learning both the procedure, but it's also learning a new grammar and a new rule for the grammar. And in particular, in that case, it's learning a rule for the verb tell, because it didn't know what tell meant. And it's learning that rule, and then it's also learning a re-ranking function for the parsing algorithm, so that despite the fact that almost every sentence you can think of has many different legal syntactic parses, it's learning an evaluation function over those parses so that it can choose the right, most likely to be meaningful one. Okay, and so here's just a simple example. I won't go into the details of the grammar that are down there, but suppose we encounter the phrase, set the subject to time to go. Then in the bottom-up semantic parse, the system, one possible parse, which the system picks, is to parse subject as the name of a field in an email. And that turns into a semantic expression. Then it can consider this and can parse that as a string. And then it can consider the preposition and make that a prepositional string. And then it can, whatever turns red next, turn the word set into set field from strings, so that in the end we get this semantic parse. And again, the details of the grammar are not as important. But the point is a bottom-up parse, which is able to both combine the component words into phrases and assemble the meanings of those phrases compositionally as well. And so because of that composition, we get kind of a natural opportunity to generalize from the very specific training episode. Tell my project team that we'll meet at 4 p.m. But after learning from that, the system has a natural generalization from there because it's learning these parse rules. So to take a simple example, suppose I say, tell Judy I'm late, and the system says, I don't understand, teach me, and then I say, create a new email, add Judy's email address, in the subject field, put I'm late, send it, then in fact, here is the parse of that sentence, which is obtained from the instructions that I gave. Basically, it's saying, you can see it here, create an instance of an outgoing email, set the recipient list to Judy, etc. And so when I give that sequence of instructions, the system assembles from my sequence of sentences this procedure, and that becomes the labeled training example of what the semantics should have been if it had been able to parse my original sentence, tell Judy I'm late. And so now here's the parse, here's the parse, but to generalize this, what happens is some of those constants turn into variables indicated in red. And in fact, Judy and I am late become variables. And the reason is we have an algorithm that says parameterize any span of text in the original sentence, tell Judy I'm late, whose semantic parse is a subtree of the full sentence semantic parse. So because I am late is a single contiguous span of text in the original thing, and so is Judy, and they happen to be subtrees in the semantic parse, they get converted into variables. And so in the end, what the system, knows is that tell x, y means, or tell argument 0, argument 1, applies in this case to tell Judy I am late. But now it also can generalize. Okay, so that's a sketch of what's going on internally. We tried this system on some people. We went to Amazon's Mechanical Turk, and we have a typing text version of this where you can interact by typing instead of speaking. And we signed up 123 people to use this. We gave them instructions to interact with an email system. For example, we said your 9th task is to create a new email and set the recipient to the current email sender. Don't type the email yourself. Use current email sender when you refer to the sender. And now the Mechanical Turk worker got to type natural language commands to instruct the system to do this. And sometimes the system would say, okay, I'm doing it. Sometimes it would come back and say, I don't understand, do you want to teach me? And then the user could say no, or yes, I'll teach you. So we tried this on 100 people, 123 people. And here's what we found. The good news, many of these subjects in the experiment, human subjects, voluntarily did teach simple commands, like they taught what forward means, or reply or next. Because they had taught these commands, on average, they gained efficiency. They would teach these commands and then reuse them in a subsequent task they had to perform. So they did, but they did benefit by teaching these commands. But on the other hand, less than half of the people completed the 20 or so tasks that we gave them. So people got annoyed or bailed out or got bored and didn't finish. So we're not there yet, but you can see the good news is Some people were able to use this to really instruct the system, but our user satisfaction must not be too great or we would have had more than 50 people complete. And in fact, when I use the system, and you saw this in the video, it's a little tedious. Because every time you say something like, and now put Judy's name in the recipient, or Judy's email address in the recipient field, it then comes back to you and says, okay, now I am inserting into the recipient field the email address of Judy. It rephrases it as a way of testing whether its understanding of the intent was correct. But that's pretty tedious. Also, to be honest, natural language understanding is not perfect here. And so there's another set of failure modes where the system simply does not understand what you're saying. And it's confusing and in the current interface, not easy to recover from that. Okay, but still, early research, this is where we are. Okay, so now I want to talk about the example that we saw there was simply to teach the system what we mean by a particular command, like tell my assistant I'm going to be busy at 4. But a lot of the motivation that I talked about at the beginning is really to allow people to write programs, which means things that the system's going to monitor for continuously. Like whenever I get an email from my project team, forward it to my assistant. So these are if-then statements of different types. And so one of the areas we've concentrated on over the last year is how can we make the system more competent at learning if-then statements that it can then monitor for continuously. And when you drill down on that, you notice there are actually several different types of conditionals. So for example, an easy type is if I say, for example, if I get a new email from fred@gmail.com, then blah, blah, blah. Well, that's easy because if you understand the language, the system will literally generate a procedure that tests whether the sender field equals that. So that's an easy one. Some concepts are things you have to define as an active sensing procedure. If it snows at night, wake me up 30 minutes early. But now you might have to teach the system what you mean by snows at night. Open up the weather app, look at the current conditions. If that says SNOW, then it's snowing. But still, it can be defined as an active sensing procedure. But the most difficult ones are things like, if I get a spam email, then, or if I get an important email, be sure I see it before I leave work. Well, what do you mean by spam email? What do you mean by important email? In fact, people can't really give a closed declarative definition of those things. But a lot of what we want to teach, and a lot of what informally we would say to each other, is in those more abstract, non-declarative terms. So one of our students, Shashank Srivastava, just completed last month his PhD thesis, zooming in just on this question of how to learn these kind of type 3 conditional concepts. And so I want to tell you a little bit about his work. So basically his approach was to he studied this problem of learning from conversation, these conditional concepts that are part of the if statement. And he looked specifically at emails and concepts you would define over emails, like spam or important email, or email from my coworkers. And so he started by generating a set of data, which you're all welcome to, it's on the web. He had Mechanical Turkers generate emails according to 7 different categories. Like category 1, contact. You're writing an email to yourself to personally keep note of a person's contact. or humor. You're writing an email to a friend that includes something humorous. So he had Mechanical Turk workers generate emails like this. Then he had other Mechanical Turk workers write down sentences that they would give if they had to teach what those emails are. Like, these emails usually close with a name or a title. And some of those were ungrammatical. These are natural language statements people generated. Okay, so he has emails now that are into these different email-oriented concepts, and he has natural language advice about how to recognize such an email. So his problem more generally is we want to learn a classifier, in this case from emails X to label Y. Label Y might be, is this a humorous email or is this an important email? We're given a small number of labeled examples. Here's an email that is a positive example. Here's one that's a negative. And a set of natural language statements, N of them, each of which describes some Boolean property. Like these emails usually end with a signature line. And then the output is, the job of the system is to simultaneously learn a semantic parser for those sentences that as a result will generate a grounded Boolean predicate that can be evaluated for arbitrary emails, and learn the classifier itself. So we want to learn both a parser to understand what the sentence meanings are, and learn the classifier to tell which emails are positive versus negative. And so that's an interesting machine learning problem because it's kind of a chicken and an egg problem. You have to learn both how to parse the sentences and learn the classification. And so what he developed was an EM approach in which the natural language statements are given, like this one. There's a parser that has to be learned, and the parameters of the parser, let's call them theta p, those have to be learned in order to define how the parser is going to work. But then given a parser and a statement, we end up with a logical form that's the output of the parser. Like this might, given the current parser, it might decide that this sentence means this, that we should look for an attachment that matches PDF. And then given this, it can now apply these Boolean features that correspond to its interpretation of the sentences. It can apply those to the individual email examples that it has, and then evaluate those features and then end up with a feature vector that describes the email, which then goes as input to a classifier. But the classifier also has to be learned. It has its own parameters, theta c. And so in Shashank's system, there's an EM algorithm that iterates between first re-estimating the parser, these parameters, so that it could update the meanings of these sentences. And then on the M step, update the parameters for the classifier and the parser. And all of this is being driven by a learning objective of maximizing the accuracy over the small number of labeled examples that are given. And there are a set of unlabeled examples in there too. So it's also looking at the expected accuracy of those unlabeled examples, but that's a detail. So you get the idea. The point is, from 50,000 feet, the point is the system must learn both the natural language capability of parsing these natural language pieces of advice and learn the concept itself. And that learning task is driven by the goal of coming up with the interpretation of sentences that maximizes the accuracy over the training data of the classifier. So, in fact, he did this, and if you compare in red, using just the labeled examples, what kind of accuracy you get in classifying the emails from the trained classifier. If you compare that against using the natural language statements of advice, then you see indeed the natural language leads to a substantial improvement in learning accuracy, especially when you have a small number of labeled examples. Obviously, if you look at asymptotically where you have an infinite number of labeled examples, then you really don't need any natural language advice. But if you want to only do a few labeled examples, then you'd better give some other advice to make up for that. Okay, so there you have it. That's kind of where we are in terms of being able to dictate to our phones what we want them to do. And if they don't understand, then instead of just saying, oh, I give up, you can say, well, I'm going to teach you. But now if you start thinking more reasonably about teaching, you notice that when we teach each other, it's not all a matter of telling each other stuff. Sometimes we show and tell. And so we have a companion project that's really being led by Brad Myers, another faculty colleague of mine, on teaching not by natural language dictation, but instead by showing. And we're in the process of trying to pull together these two. So let me show you a video of Brad's component of this system. And this one I think I can do this way.
Order a cappuccino.
Order a cappuccino.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, order a cappuccino, what shall I do first? Say demonstrate to demonstrate.
Demonstrate.
Whenever the user gives the agent a command that the agent cannot understand or doesn't know what to do, the user can teach the agent by demonstrating how to perform a task using any third-party apps installed on the phone. In this example, the user demonstrates how to order a cup of cappuccino using the Starbucks app.
Order a cappuccino.
Executing.
The agent learns the task and is now able to automatically manipulate the Starbucks app to order a cappuccino for the user. From only one example of demonstration, Shibboleth can also determine the parameter in this task from the user's voice command and find all the other drinks it can order from Starbucks by analyzing the structure of the app's user interface. As you can see, the duck icon on the screen is now clicking on behalf of the user to order a coconut milk mocha macchiato. This work will appear in Kai 2017 and was supported by Yahoo.
Okay, so you get the idea. That was, in fact, sped up a little bit because Toby Lee, the PhD student who was doing this, I told him I needed a short video. And he said, well, I have a 5-minute video. And I said, no, it has to be 2 minutes. So he just sped it up. That's why you got to see it that way. But you get the idea. You can see that by showing sometimes is easier than telling. And for other things, it's easier to tell. So, and in fact, when we teach one another, we do a combination of those things. And so what we're trying to do at this point is now put together these two kinds of capabilities into a unified system where you could teach, for example, if it snows at night, wake me up 30 minutes early. I might want to demonstrate, look, you just open the weather app and here where it says current conditions, if that says SNOW. And it might be easier to show and speak at the same time as a way of naturally teaching this system. So that's where we are, and in terms of where we're headed. So I think of this research as at the first steps kind of stage, but I'm excited to describe this to you because I'm hoping that I can entice some of you to get involved in this line of research because I think it really has a chance to fundamentally change the way that people interact with computers or even the way that people think of computers. Right now we think of them as these fixed things that we get to use and they have certain capabilities and That's it. We have to, if we're going to team with them to do something, for example, at a work job, then it's our job as the humans to customize ourselves to fit that rigid, fixed set of capabilities of the computer. But if instead you could just teach your computer how to help you, I think it would fundamentally change the way that people in computers form teams. So what are some of the research issues? Well, one, as I mentioned, is we want to integrate verbal and showing and telling. We started collecting protocols of people just showing and telling. We don't yet have a computer that works very well to respond to that, but just collecting data to find out what kinds of combinations of gestures and verbal things do people generate. And what we find is that a lot of people, fortunately, use the verbal channel to give hints about what's important and how to generalize. So for example, if they're teaching the system to order a cappuccino, they will demonstrate, like you saw in the movie. But they'll say things like, oh, right now I'm pulling down the menu and I'm choosing cappuccino, but obviously you could order any of these drinks. Right now I'm paying with PayPal, but obviously if you have a credit card, you can type that in. So that's some of the helpful kinds of things that people say. And so it might actually turn out that if we allow people to both show and tell, we actually might make the learning problem on the side of the computer easier, because people, and the great thing is people naturally know how to teach other people. And so we just want to build a computer interface that can piggyback on that competence that we all have. So that's one research issue. Another is, can we share what's taught across different phones? Once I teach the system what it means to tell my wife that I'll be late, you shouldn't have to teach the system what the word tell means. Or maybe you do, because maybe I say tell my wife means to send her an email, but maybe you want to, whenever you use tell, you want to use a text message. So there's an issue of different semantics that different people might have for the same utterance. So that's an interesting research direction. Incremental refinement. When I said it several times, you probably didn't notice, I was being overly vague when I said if it snows at night, wake me up early. But if I told you that as a person, you wouldn't wake me up if we just had snow flurries. Because you probably inferred that my reason, what I really meant was, if it snows enough to mess up the traffic at night, then wake me up 30 minutes early because I don't want to be late for work. But I didn't say that, and as a human, you used your common sense to fill in what I probably meant, and you'd probably execute correctly. But if I have a computer without common sense, the first time it snow flurries and it wakes me up, I'm going to want to incrementally refine that instruction if it snows a lot. Or maybe what I really want to do is, instead of saying if X, then do Y, maybe what I really should do is if X, then do Y because Z, because I don't want to be late for work. Or if I'm somebody else from a tropical climate, I might give the command, if it snows at night, wake me up 30 minutes early because I've never seen snow and I don't want to miss it. It's a different intended generalization. So, and in the spirit of conversation rather than monologue, it would be quite reasonable for the system to come back if I say, if it snows at night, wake me up 30 minutes early. It'd be quite reasonable for the system to say, oh, why? To elucidate that reason from me so that it could generalize in the way that I really intend. Mixed initiative, teaching dialogues. So in the videos you saw before, the user is in control. It's really a one-way dictation, whether it's a demonstration or a spoken thing. In both cases, it was the user who owned the conch shell. It was the user who took the initiative. But in real conversations between people, there are clarification dialogues and mixed initiative. So in the end, I think and I'll end here, I think this line of work is going to be important for us because now that we have conversational interfaces to devices and we're getting used to using them, sooner or later we're going to wake up to the idea that we can use these for more than invoking pre-existing functionality. We can also use them for a kind of programming. So I think it is going to be an important thread. But this is still even just a piece of the overall broadening of machine learning that I think we're going to see over the next decade. So if you go back to the original idea that if you want to know the future of machine learning, just look at the things that, the ways people learn that computers don't yet, then you notice people actually are pretty good at combining statistical learning from passively observed data, verbal demonstration, and experiments. People also just play and try stuff and see what the outcome is. You want to be a little careful doing that on somebody's phone, but within bounds, this is another one of the ways in which people learn that computers don't very much yet. Okay, so that's what I have to say. Thanks for your attention.